Ok. Boa noite a todos e a todas. Vamos dar início à sessão do seminário da professora Zadé Mohammadi. Queria agradecer de novo. Eu estava, antes de entrarmos no ar, eu estava agradecendo a Zadé por ter vindo, atendido a solicitação. Ela tinha dado um seminário para a gente há um tempo atrás e, de modo muito prestativo, atendeu o convite. É uma honra. Vou falar algumas coisas assim do currículo dela, mas a reputação é muito boa. Assim, pelo menos como chegou, é a jovem talentosíssima que está em Recife. Mais ou menos assim. Bastante deferência, como chegou, assim, né? E no seminário, dá para ver, ela é muito ativa, e ela veio para o Brasil em 2014, veio da Pérsia, estávamos falando do Irã, veio da Pérsia, fico, em nome de todos, fico, de fato, muito honrado. Ela vai dar o seminário, depois as pessoas podem postar as perguntas, eu vou ajudando a administrar. Tem o pessoal, assim, por detrás também, o Eduardo, que está acompanhando, etc. Se tiver algum problema, eles nos ajudam. A professora Zadé possui graduação em Física pela Universidade de Sahih Barreshit, acho que é assim, eu não sei a pronúncia, desculpe-me, mestrado em Energy Physics na Universidade de Mazandaran e doutorado em Física de Altas Energias pela Universidade de Sahid Barreshti. Atualmente, isso em 2013, atualmente é professora adjunta da Universidade Federal de Pernambuco. Tem experiência na área de física, com ênfase em física de partículas elementares e campo, atuando principalmente nos seguintes temas, com Soliton, Fermion-Soliton, os sistemas de Fermions e Solitons, os Kink Interactions, Cosmic String, Casimir Energy, Casimir Effect at Finite Temperature. Eu estou lendo o texto do Lattes. A professora, como eu disse, veio para o Brasil em 2014. Inicialmente se juntou com o importantíssimo grupo da Universidade Federal da Paraíba, depois teve em Campina Grande outro boníssimo grupo também, assim, muito ativo, falo meninos, assim, porque tem muita gente jovem, dos dois lugares, a Universidade Federal da Paraíba, o Instituto do Departamento de Física, tem pessoas bastante atuantes na física no país e no mundo, sem dúvida nenhuma. E ela começa por ali e depois faz o concurso e se estabelece em Pernambuco, também num importante instituto de física para o país, para a gente. É uma honra, a Zadé, estar aqui de novo e vou passar a palavra para você. Eu vou desligar a minha câmera, que aí fica o foco todo para você, tá certo? Se tiver alguma dificuldade, alguma coisa assim, é só dar um toque, ou levanta uma mão, alguma coisa assim, a gente atende. Muito obrigado de novo por atender a conferência. Até logo. Isso.
Muito obrigada, professor Ademir, honra é minha, e obrigada pelas palavras. Desculpa, eu não preparei em português, eu vou mudar para inglês, ok? Mas no final, se alguém quiser, posso explicar em português. Ok, so the subject I'm going to talk about today is the solitons. I will introduce the subject. I'm not going through the detail of each of the existing solitons, but I will talk more about the relevant ones in our work. And then I will talk about the interaction between the solitons and the fermion field present in the system. Okay. Okay. So First of all, I will introduce the subject of soliton in 1+1 dimensions, which are called kinks. And then I will introduce it, I will generalize it to higher dimensions. I will focus mostly on cosmic string because it's relevant to the works I'm going to talk about, our works. And besides that, in the Fermion-Soliton systems, in some of them we studied the Casimir energy and Casimir effect. So I'm going to introduce a little bit what is Casimir energy and what we calculated. So this talk is based on 3 papers that we have on the subject. First one is from my PhD project. So it's older, it's from around 2013-14. But the last 2 are quite recent. They are from last year and this year. So first, let's see, what do we call soliton, okay? Okay, based on, this is the majority of people agreeing in the literature, at least in high energy physics, so I will just summarize it, the ones people agree more. So there are 2 subjects, solitary wave and soliton. Solitary wave is an isolated pulse. So it is, the energy density is localized, and if you sum over in the whole space, the energy will be finite. And when it is moving, it doesn't change shape, which is, if these systems were not non-linear, this was impossible, because a dispersive system, as you know, if you create, for example, if you threw a stone in water, you will see the water wave gradually disappear in the system, so it doesn't keep the shape. But if you add one more ingredient to the system, besides the dispersion, if you include nonlinearity, in some specific systems, the nonlinearity compensates the dispersion. So, because, for example, what is dispersion? Dispersion is related to the speed of the wave is related to the wavelength, but nonlinearity relates the velocity to the amplitude. So these 2 effects, they can sometimes compensate each other, balance each other to have a constant shape wave moving with constant velocity, okay? So this is what I talked about, it's solitary wave, okay? To have a soliton, this is much more restrictive. It has much more restrictive condition. It is when you have some of these solitary waves colliding. In the middle, there can appear a lot of nonlinear effects. But after leaving, if you look at just the asymptotic future, if they recover the shape again, then we call them soliton. This is characteristic of integrable systems, okay? This is due to, because what we are talking about, we are talking about the fields, because, for example, if you create these waves in water, what is important here, the differential equation is about the amplitude of water, okay? That gives the wave. So this is the amplitude at each point can be different, so you can define a field. So if you define a field, it means that you will have infinite degrees of freedom. But there are some systems or some differential equations that there are infinite first integrals or constants of motion, which is behind them, it's the infinite symmetries behind the system that makes them integrable. So after the collision, they recover the shape. So because of that, there are many physicists and mathematicians that are interested in this subject, because somehow the system behaves, although it's nonlinear, behaves somehow at the asymptotic future, behaves like linear system. It separates like as if it was following superposition principle. The picture here you're seeing, it's from 1995. It's the recreation of an event that gave origin to the whole story of Soliton, which was one it was an engineer in 1834 called John Scott Russell that saw this kind of wave when one boat stopped, created one bump of water. He was on a horseback and followed the wave for 3-4 kilometers and then saw that the wave is not changing the shape. So became interested because based on the fluid dynamics models existing till that time, this was not possible. So he devoted most of his life to this subject to recreate this and study the behavior, how they work, but more experimentally. But after him, there were many physicists and mathematicians. They studied the system more systematically, modeling the system mathematically and understanding how these nonlinear systems work. Okay. So now to see the simplest case possible you could consider is in 1+1 dimensions, okay? Then I will give motivation why even this is interesting, okay? Because obviously we are living in 3+1 dimensions, but then I will give some motivation, and besides that, it's a toy model for higher dimensions. So you will see that this can be still interesting to study. And there are a lot of effective models that they are effectively one-dimensional, so they are relevant in this aspect. So the simplest case, if you have scalar field, real field, and for example, if I choose the potential in the form of this phi-4, okay, this is called phi-4 theory or lambda phi-4 theory. The potential has two minima, as you can see here, okay? These minima that you see in the potential, they are called trivial minima because they are not x-dependent. You see obviously in the as minima of the potential. But you can show that in specific systems, if you solve the system besides this minima, the trivial minima, there can be other types of solutions that they are connecting the two minima and they are still a solution of the system. For example, for phi-4 theory, if you solve it, you will see tangent hypershape that if you plot it, you see it goes in -infinity, goes from one trivial minima. It connects one trivial minima to another trivial minima, okay? And it is x-dependent, so it is called non-trivial solution, okay? And then you can study the energy and energy density of the system to see that the energy density, you can see it is localized. As I explained, you can see exactly like an isolated pulse that the energy is concentrated around the center of it, okay? So it is localized. So in this case, you will see that the energy of the system is finite. The energy of the solitonic system is called soliton mass, okay? But you see that the energy of this system is higher than the trivial solution, the trivial minima, that they are at zero. For example, in the phi-4 theory, we showed that. Let me show you again. Here, you see the minima are at zero, okay, at the origin here, but the energy for these non-trivial solutions are higher. So we should see that what really protects the system against decaying to these trivial minima, because if there is a chance, system will go to the lower energy, okay? So what does protect this system from decaying to trivial minima, okay? For this, you can see that there is another thing associated to this system, which is they are topologically protected. What does it mean? It means that you can, if you look at the concept of topology in mathematics, you will see that they are belonging to non-trivial homotopy group, okay? Okay. I will just explain really fast, but the detail doesn't matter. If someone is interested, then can look up how this works. So it is related to non-trivial homotopy group, which is related to the non-contractible, distinct non-contractible M-sphere in the vacuum manifold, okay? So these vacuum solutions, they give vacuum manifold, okay, these kind of solutions, okay? So, for example, in the case of this 5-4 kink, you will have the minimum at the two minima here that I showed in the potential. Okay, so you will have two disconnected pieces in the vacuum manifold. Okay, and the number of these disconnected pieces somehow is related to a topological charge you can associate to this system. And this topological charge, if it is non-zero, it can never decay to zero. Okay, so it is topologically protected. So how do we see how we can relate it to the topological charge, or in topology even it is called winding number? Okay, so for example, for this system, you can have topological charge, then you can show that it is partial mu of this k mu is zero, but it doesn't mean anything because it's not coming from Nether's theorem, so it is not related to the symmetry of the system. Actually, it's reversed. It's related to the spontaneous symmetry breaking in the system. So the zero component of it is what matters for us. The zero component, you can show that it is related to the value of the field at infinities, okay? So in the middle, how you change the shape of this kink doesn't matter. You can change it the way you want, keeping the boundaries the same, and still having the same topological charge. Okay, of course, when you change the shape in the middle, all of them, they will give, if you keep the boundaries the same, all of them, they will give the same topological charge, but obviously some of them are higher energy than the others, so the system will decay to the one that gives the lower energy, okay? But this is never possible for the system to decay to the trivial vacuum, okay? And actually, this can be seen here. This can be seen as this soliton goes from minus infinity to plus infinity. If you want to change one minimum to take it up to be just trivial vacuum on top, or take the one on top down to have the trivial vacuum just in a negative value, then to change in the whole space to infinity, this costs for us infinite energy. So infinite energy means that it never happens, okay? So the topological charge part, it's what mathematicians understand from this system, but from the point of view of physicists, you can see that this will cost infinite energy, so it won't decay. So the system is topologically protected. Okay, then you will see that this is really important in the system. Okay, so let's get back. So as I wrote here, the topological soliton is the one with a topological charge which is non-zero, and the non-topological one is the one that is the topological charge equals zero. Okay, so even you can have a configuration that is not trivial vacuum, but the value of the field at infinities are the same. Still, you can show that because of the value of the field at infinities to be the same, the subtraction will give zero. So it is trivial configuration. So because the energy is higher, so the system will decay to the trivial vacuum in this case. Okay. So if Q is zero, it means that there is no protection. The system always prefers to go to the minimum energy. Okay. Besides that, there is another subject which is important for the stability of the system, besides the concept of integrability for the collision that I introduced and the topology of the isolated kink that I introduced. There is another subject important in the stability of the system, which is called BPS, after three physicists, Bogomolny, Prasad, and Sommerfeld, okay? Or it is called self-duality condition also, which is there is first order differential equation which solves your second order Euler-Lagrange equation, okay, which is always valid. It is, you can prove that for 1 + 1 dimension, this is generic aspect of 1 + 1 dimension, so this is always valid. So you can always find first order equation that solves second order equation, okay? So in this case, you can define the potential as 1/2 of another type of potential, which is called superpotential, derivative of it with respect to the field, then square it, okay? This superpotential is called superpotential because the concept is coming from supersymmetry, but it is completely irrelevant here for us, okay? So now you can play with the energy of the system. That you can see that the first contribution here is always non-negative, which means that the minimum of it is when it is 0. So if you put this first contribution equals 0, which means d phi dx to be equal w phi, then we say that it saturates BPS condition, okay, because the energy of the system is at the minimum, because if it is non-negative, so if it is higher than 0, it always increases the energy. So the one that gives d phi dx equals w phi gives you the minimum energy. Because of that, the BPS condition actually is important because of the stability of the system, because it gives the minimum energy. And more interestingly, the energy in this case is related to that topological charge or winding number that I introduced before. Okay. Now, to give, I always give this motivation to, because I really like this model. Okay, there is. I want to show that there is motivation besides being a toy model for higher dimension, these 1+1 dimensions that we study, and besides being an effective model in many systems, you could actually see it in some specific systems. For example, in a polymer called polyacetylene. Okay, in polyacetylene, you have layers of atoms that the electron can move in each layer but can't hop to the other layer. Okay, so in practice the system turns into a one-dimensional system, spatially speaking. Okay, so in this case, if you in this case normally you would expect each atom should oscillate around atom site, okay, because of many reasons, because of the effect of temperature or because of the effect of zero-point motion in the system. So you would expect always there is oscillation. So the atoms would oscillate around atom site. But interestingly, the atoms they don't oscillate around the atom site. They go a bit to the left, to the right, or a bit to the left, and then oscillate around this new point. Okay, then imagine the system has reflection or parity symmetry. So going to the left or to the right is arbitrary. So the system doesn't choose one over the other. So randomly in different regions, the system chooses to be going to the right and oscillate, and going to the left and oscillate. So let's call one of them vacuum A and another one vacuum B, okay? And then there are different domains here with different vacua, okay? One of them going to the right and oscillate, and one of them going to the left and oscillate. And the point is, when they see each other, these domains, in this part that they go from one configuration, one vacuum configuration to another vacuum configuration, you could create a soliton, okay? If you consider the displacement here as your scalar field, okay? Then you can see that you can show it as a kink like the one I showed for phi-4 theory, okay? Going from one vacuum to another, or the other way around. One of them is called kink, another one is called this one called anti-kink. Okay, but this doesn't matter. Okay, and then you can show that the energy density of the system, it is exactly with two minima, and then it really behaves like phi-4 theory. Okay, and this whole thing is called parallel instability. Okay, so you can see that one motivation is really in a system. You can see this is really happening. You can model it with this kind of objects. Okay, so if you consider this kind of object in higher dimension, I mean higher than 1+1, then imagine you have a kink in higher dimension, in the other dimensions to be trivial, okay? Then you will create domain wall. Then there are 4 types of domain wall, but it doesn't matter for me at this point, okay? Like, for example, if you look at the magnetization in the systems, and imagine the different regions here, as it is shown here, it can have different magnetization, and the wall separating these different magnetizations, it is called domain wall. That is exactly one of these 4 types, okay? So another application of these kind of domain walls or kinks is in, for example, in optics, okay? You can see these kind of waves, for example, they're called bright and dark solitons in optics. Bright is the one that the intensity of light at 0 is maximum, and the dark one is 0. The dark one is the topological one, so it is more robust against the perturbation in the system, but it's more difficult to handle for the experimentalists. Okay, but anyway, people work in optics with this kind of solitons. They, for example, they pick a normal wave with constant intensity, and at some point they turn off the intensity, create this kind of dark solid, the dark solitons, and then they observe the propagation of these kind of waves. Okay. Then in higher dimensions, besides this kind of object like kink or domain walls that we saw, there can be really different solitons appearing. Behind all of them, there is spontaneous symmetry breaking or phase transition, okay? Phase transition in the sense that, for example, this potential that I showed that has 2 minima, for example, here. If you look at the potential is symmetric, but if you sit in one of the minima, what you see around you is not symmetric. So if you choose one of these minima, the symmetry of the system at the level of the vacuum is already broken. So this is called spontaneous symmetry breaking, okay, which happens at the phase transition point, okay. So one of the other applications, it's for example, in cosmology, okay. We know that early universe was really hot, so people believe that the universe, when it was expanding, the temperature was dropping that fast, that was creating phase transitions or this kind of, and as remnant, this kind of defects. Okay, for example, there could appear, we believe there appeared something like cosmic strings. Then I will explain what is cosmic string, or monopoles, or textures, or many types of solitons there could appear in the early universe. Okay, actually there are many observations and happening now. To actually the more hopeful ones is the most hopeful one is the cosmic string. Okay, cosmic string. It's not difficult to see how it is the shape. Okay, for example, if you have a bottle of water and you freeze it, then you will see that in the middle appears a lot of cracks that they are really similar to these cosmic strings that we expect, like in the early universe. Because of these phase transitions, there appeared fractures in space-time, created this kind of cracks that we call cosmic strings, that they are extremely heavy objects, okay? They are extremely thin. We would expect below the size of a proton, but really long ones. Okay, for example, if you have like around 1 kilometer of this cosmic string, you already have the mass of Earth, okay? So it is that massive that when it is these kind of cracks, they interact with each other, they can get around themselves or create, they can join with the others and create some loops, and the dissipation of these loops, we would expect to create a gravitational wave. and we would expect at some point to be able to detect them, okay? Based on the theories existing, we expect even after the inflation they could appear. Based on the quantum field theory and string theory, we would expect even after the inflation there appeared these kind of cracks in space-time, and we would be able to observe them at some point, okay? Actually, then I will comment on one recent observation that there is a chance that it is the detecting the cosmic string, okay? Okay, so as I said, you can imagine them as the cracks in the water when what happens in the water. You have translational and rotational symmetry in the system. When you decrease the temperature fast, different regions of water start crystallizing, so loses the continuous symmetry of translation and rotation, and we'll have discrete symmetry of the crystallized ice, okay? But in different regions, and so different regions means that each of them stay in specific vacuum, but when the size of these ices appearing in the water increases, at some point they meet. When they meet, in the junction of this meeting appears this kind of walls. It's not a domain wall, it's called, in this context, it's called the cosmic string, okay? That joining the trivial minima appearing there, okay? So I think this way it's simpler to imagine them. Then, okay, they are like vortex lines that they appear, like, for example, in flux tubes in superconductivity, and they can appear as vortices in superliquids like liquid helium, okay? And the theory behind them, it's exactly the same theory as vortices in condensed matter. For example, the simplest version of them, because there are many cosmic string theories, okay, the original and the simplest version of them is these Maxwell-Higgs vortices, okay? And this potential, and obviously you can see that this F is, we introduced the gauge field here, okay? And then if you look at the potential, if lambda is negative, the system has just one minimum, so there is no chance for the phase transition, okay? But if you gradually increase lambda to pass zero and be positive, in this case, the system starts having these infinite minima, okay? That gives this is exactly when passes from negative to positive appears this phase transition. And if you go to each of these minima, then you see, you don't see the symmetry of the system. The symmetry will be spontaneously broken when you look at one specific minimum, okay? For example, this lambda appeared, just to get back to see this potential that we have here. So the negative lambda here, there is no spontaneous symmetry breaking, so there is no vortex or cosmic string. But imagine this lambda, for example, we have this model for the early universe. Imagine this lambda is dependent on the temperature. Imagine I decrease the temperature to the point that lambda becomes positive, okay? In this way, I can create these infinite minima and create this kind of cosmic strings as remnant, okay? So, if you look at the minima here, there is infinite minima that they are given by this relation, obviously, okay? This eta is the one here appeared, sorry, this eta is V here, okay? Sorry, I changed the notation. Okay, so phi is V times exponential of I theta, because if you go around this circle, you will see the same. So, I mean, energetically, it doesn't cost any energy if I go around this circle, okay? So they are, there is infinite degenerate energies here, okay? So, but this is what we had for vortex, and this then people picked this concept in condensed matter with these vortices, took it to cosmology, okay? they looked at this gravitationally, okay? So you could translate that, that potential to a metric that in a simplest case, you could have one cosmic string with 0 width and with infinite length, okay, which the line element is given by this relation, ds squared that you see here. It's quite simple line element. It is exactly like Minkowski. The only difference is if you rewrite the angle with this phi prime, you will see that the angle won't go from 0 to 2 pi. It goes, in principle, is more probable to go below. So there is deficiency here, but there can be, in principle, I mean, mathematically speaking, it could be more than 2 pi or less than 2 pi. More than 2 pi actually is really difficult to imagine, okay? So let's look at the less than 2 pi. So what do they mean topologically? Imagine you have this kind of strings and the space-time around them doesn't complete the 2 pi. So it means that, like for example, you have a piece of cake, you have a cake. You cut a piece of cake, okay? Then if you separate this piece and then identify the edges, what happens? You will have a conical object, right? Then, so because of that, the space-time associated cosmic strings are called conical space, okay? So they can be really interesting because this conical structure of the space-time gives chance to observe this kind of topological object, for example, with a lensing effect. Because if imagine the same star you're identifying from left and from the right, you identify the points. So it's like, it looks like the lights are coming from really different places, but actually it's just the topology of the space-time make them look like this. So there is this lensing effect. So the hope is, or you can observe them through the lensing, or you could observe them through this cut and paste and creating these loops, and the loops start oscillating and gradually losing energy as gravitational waves. So with the experiments of gravitational wave, we would expect to observe them. This is one of the opportunities that we can invest on. Okay. Actually, this is the one now that recently appeared for a group. They are called Nanograph, okay, which is abbreviation for, if I'm not wrong, North American Nanohertz Laboratory for for Gravitational Wave. Okay, they observed for more than 12 years. They collected data. They observed pulsars. Pulsars, they are the rotating stars that they could be like neutron stars or white dwarfs. Okay, so, and they are extremely precise. They eject in the poles. They eject radio waves. Okay, and whenever these radio waves coming to us, it becomes visible in Earth. We will look at the period of this appearing again and again, and this period is extremely precise. Actually, this is the best clock we know. Okay, so if the clock is not working well, something is happening in the middle, right? I mean, if the period is not as exact, some perturbation happened in the middle. Okay, so this is actually the case for this group. They put the paper. They sent the paper for being peer reviewed, but still is not finished. Okay, it appeared in September this year. That if the perturbation is not through the noise that they think is highly probable that it is not, the best explanation for this they expect to be gravitational wave. And the gravitational wave, it could be like colliding black holes or neutron stars or anything like this, but the behavior, it looks more like cosmic string. Okay, so if they can prove it, actually, this will be extremely interesting and important discovery, I think. Okay, so this is what this group is hoping, and actually I'm hoping they can observe something. So, okay, so this was up to this point. I wanted to introduce some of the solitons that we had contact with, I mean we worked with. Okay, there are many other types of solitons in condensed matter, in optics, in high energy physics, but I'm not going through them because they are irrelevant for our works. Okay. Besides the concept of soliton, I need to introduce another subject. It is called Casimir effect or Casimir energy, or the force associated to that. It's called Casimir polar force. Okay, actually at some point they work together. So this effect is purely quantum effect. Okay, classically there is no explanation for them. Okay, and it is due to the explanation comes from the second quantization. So with the second quantized field theory, we could explain the effect. What is the effect? This was Casimir proposed theoretically in the beginning, that if you put, for example, if you put like this, if you put, for example, two parallel metallic plates that they are not electrically charged, okay, and if you put them really close to each other, imagine below micrometer or a few micrometer or even going below that, okay, they start attracting each other, but there is no external field in the system, so there is no explanation classically for the force that is coming from which kind of field. Okay, so this was mathematically proposed by Casimir, that expected this attraction would appear. In general, if you pick different geometries and different dimensions, it could be attraction or repulsion depending on the boundaries of the system. Okay, but for this specific one, it is attraction. Okay, and even actually, this is behind what we know as van der Waals force. Okay, that the atoms they attract each other a little bit, but they are neutral. So the thing behind them, we think that it's coming from the Casimir effect. Okay. And then, okay, how do we explain them with second quantized field theory? Okay, so let's get back here. In quantum field theory, each field you could expand them as each mode of it as a harmonic oscillator mode, and then sum over infinite modes, infinite harmonic oscillator. Okay, and then when you sum over infinite harmonic oscillator, even if you are in the vacuum state, okay, even if the system is not excited, sum of this h for omega over 2, if you sum over infinite modes, it will diverge. Okay, so it will give a divergent quantity, which is actually one of the biggest problems to unify gravity with the other forces that we can formulate them with quantum field theory, because the explanation normally is that, okay, this infinite energy doesn't matter. What matters is always you should choose a reference energy and just compare with this reference. The reference can be at infinity or any point I want. Okay, but unfortunately gravity sees all the energy existing, because for gravity, energy and mass are the same, and all energy are relevant in the system. So this infinity actually is a problem of quantum field theory, but anyway, in this case is not problematic, because what matters is you have, for example, vacuum, and then you put these two metallic plates, for example, so you put boundary in the system, and this boundary will change the fluctuations of the vacuum and creates this pressure or toward each other or the other way around, which can create attractive force or repulsive force, okay? So in this case, it's attractive, okay? And then there are a lot of interesting applications actually for that. Okay, but what we are more interested in is more theoretical part of it, okay? So now I want to talk about the first Fermion-Soliton system that we studied. That I said it's from my PhD project, okay? This is a fermion interacting with a background soliton. Background in the sense that fermion will see the effect of the soliton, but soliton doesn't see the effect of the fermion. It's not a really bad approximation because you can show that solitons actually are really heavy in weak coupling. And because of being really heavy, they are, you can, most of the time you can consider them as classical object, okay, which is they are that heavy that they don't see the effect of the other fields, but the others, because of that, will see the effect actually strongly sometimes, depending on the weak coupling regime you're working or strong coupling regime. Okay, so in this system, it is a non-trivial interaction between the Dirac or spinor field here with this phi of x, the pseudoscalar field here, which we chose it to be sine-Gordon-Soliton. Sine-Gordon-Soliton actually is really interesting, important, and actually it is historically the first integrable system known mathematically, which is to explain the surfaces with constant negative curvatures, okay, explains them. But then it appeared in many physical systems, and because of being integrable, they are actually really interesting. And you can study many particle-like effects with these kind of solitons, okay? So in this system, we want to consider this sine-Gordon-Soliton as the background here. So there is no dynamics for this phi of x, okay, that affects this fermion field here, okay. Then you are not. Then we consider the solid line here is the sine-Gordon. We considered another toy model that it is simply three pieces. It's a constant at infinity, and then another constant here, and in the middle is mu x, okay, simply, the slope is mu. That it is mimicking a kink, okay. And why did we do that? This toy model actually is really interesting because you can solve all for the system, for the fermionic system, you can solve for all the bound and continuous states analytically, you can find them. And actually even the Casimir energy partially can be solved analytically for this system. So we used it as a checkpoint and even sometimes for initial condition for our numerical method. And then we compared the results, okay? So I'm not going through how we calculated these, the energy spectrum. This is the energy spectrum. The solid line again gives the energy spectrum for the fermion field with the sine-Gordon-Soliton as the background, and the dashed one is from the toy model, okay? So the plus and minus, they are positive and negative parity lines. You can show that each line separates with specific parity, okay? They don't mix up, okay? And the system has parity symmetry, so at the end you could study the eigenstates of parity, the parity eigenstates of the fermion field, or the scattering ones that they are the physical ones, okay? We did for both. And then there is one interesting point here in 1+1, the relativistic 1+1 Dirac equation. You can show that in the Dirac equation without the interaction, there is one half-bound state with positive parity here on top, matching the mass. And there is half-bound state here below with negative parity, okay? What is a half-bound state? Half-bound state is the field going to the constant at infinity, but is not going fast enough to be square integral, okay? So they are not normalizable, this kind of states, okay? But you can show that for the non-interacting Dirac equation, there is one half-bound state with positive parity here and one half-bound state with negative parity below. And then when we switch on the interaction with the soliton, then the one here below sinks. I'm using the language, Dirac language. You have Dirac C and you have sky. C is the one with the negative energy and sky is the ones with the positive energy. Okay, so the one with negative parity sinks in the C and the one with the positive parity appears as the bound state when you switch on the interaction with the soliton. Okay, so then there are two possibilities to do the expansion for the fermion field. One of them with the eigenstates in the absence of the background field in the free case, which is the first line here, okay? But then you could do differently. You could expand it with the ones in the presence of the soliton. So you will have the continuum states with positive and negative energy, and you have the bound states. And people showed that this is still complete basis, okay? Because you should expand in complete basis of the solutions, okay? So we could expand with this free case, or in the presence of the soliton with the continuum or the bound states, okay? So if we do that, what we are interested is the Casimir energy. To find the Casimir energy, we need to find the Hamiltonian, and then to sandwich it between the vacuum, okay, in the presence and in the absence of the soliton, and the subtraction will give us the distortion that the soliton created, okay, in the spectrum, okay. So we will get the Casimir energy. So to do that, first I should construct the Hamiltonian of the system, okay. So what did we do? We expanded the psi and psi dagger in the presence of the soliton, okay. And then we know that this is called one particle Hamiltonian, okay. So the one particle Hamiltonian will extract the energy of the state, okay, because of that appeared the square root of the momentum squared plus mass squared here, okay. For the positive energy, it is with positive sign, and with the negative energy, it's with the negative sign. And it extracts from these bound states, extracts the bound energy, which is, it can be positive, we call it sky, and it can be negative energy, we call it C. Okay, so now that we have the Hamiltonian, I could find the expectation value of the Hamiltonian in the non-trivial vacuum. Non-trivial vacuum is the vacuum in the presence of the soliton. Okay, then you can see that the only term surviving is these two terms. Okay, and these two terms are just you can see that the only relevant ones are the negative energy ones, okay? Then you can prove that, you can show that. If the system has charge conjugation symmetry, then you could write it or with the negative energy states, or with positive energy states, or half of each. It didn't matter. If you have charge conjugation symmetry, which is the symmetry in this system, okay? But systematically solving it, you can see that the negative energy ones are the relevant ones, okay? The other one is just the consequence of the symmetry. So now to find the Casimir energy, I need to subtract the expectation value of the distorted Hamiltonian, I mean the interacting Hamiltonian, in the non-trivial vacuum, from the free Hamiltonian in the trivial vacuum. If you subtract them here, then you both of them diverge, okay? But to take out the divergence, you can show that the divergent part of the non-trivial one is exactly cancelled, is cancelled by the divergent part in the trivial vacuum, the expectation value of the free Hamiltonian in the trivial vacuum. So what survives is our Casimir energy, which is finite. Okay, so we put them together. So we already found the relation for the Casimir energy, okay, which is sum over all negative bound states, and then this rho is the density of the states, okay, in the presence of the background field, the soliton, and in the absence. We put them just together and subtracted them. And this m over 2 is because of the presence of the half-bound state in the trivial vacuum, okay? Then you subtract minus m over 2, so it will be plus mass over 2, okay? So then for the case of the toy model, it is possible to solve almost everything analytically except one integral for the Casimir energy. You need to do it numerically, okay? But it's a simple integral. But in the case of the sine Gordon, we don't know the density of states. We don't have a explicit form for that. We use the trick. We know that the difference of this density of states is related to the derivative of the phase shift, okay? Phase shift is, in principle, is dependent on the momentum, and the derivative of it gives this difference. So we use the phase shift method to calculate the Casimir energy, and then, okay, this delta is the contribution of the phase shift for the positive energy continuum that we have and the negative energy continuum that we have, okay? Or you could write it based on, you could write each of them for each parity, okay, for each parity eigenstate. As I said, the system has parity symmetry, so this is relevant. Oops, sorry. So here, we used the theorem to check our result for, we calculated the phase shift, but how do we know it's correct, the result, okay? What did we do? We used a famous theorem called Levinson theorem, which is relating the difference of the phase shift at zero momentum and at infinity. This zero and infinity is the momentum, okay? You can relate them based on this theorem. You can relate them to the number of bound states in that specific configuration that you are, okay? The NT is the threshold or half threshold bound state, or it is called the half bound state that I said that it is going to the constant at infinity, but it's decaying not fast enough to be square integrable. So the number of these kind of states matter, and these states normally appear in the junction between the bound and the continuum, in the interface they appear. Okay, so then our check for our phase shift was this theorem. Okay, for example, you could look at these results that we have the phase shift, okay? So you can show the Levinson theorem for the general phase shift, and it is valid even for each parity, okay? So you can look here for both cases. So you should sum this negative parity phase shift with this negative parity phase shift, and then look at the number of the bound states appearing, okay? And then the difference from top to below, it should be matching the number of the bound states. And in this case, you can show that it is they exactly match for each parity and for the total, the scattering one. Okay, just you need to sum them and see, like for example, here it is 1.5 and here it's 1. So the difference is 0.5 plus this minus 0.5 minus 1 gives 0.5. So the sum of these two, the difference gives 1, and you can show that n is 2, the number of the bound states, and the number of the threshold states or half-bound states in the trivial vacuum is 2. So checking this relation, it will be 2 minus 2 over 2, which gives 1. Okay, so the result is matching the theorem. Okay, so in the whole process, we were always checking with the Levinson theorem the phase shift that we found, and then we replaced the phase shift inside the calculation of the Casimir energy, and we found the Casimir energy. Okay, we have two graphs here. The left one is for each parity. The solid one is for the sine Gordon, and the dashed one is for the toy model. Okay, so you can see for each parity we found the Casimir energy. You see this oscillation, okay? Then I will say what it is. Actually, when we found these oscillations first time, we thought that our program is not working. It's with error. Then when we repeated and we made it with higher precision, we saw that it is always appearing these oscillations. But interestingly, these oscillations appearing in each parity, when you sum them, you get it for the scattering states. There is no oscillation in the scattering state. So physically, they are not observable. Okay, but we think this oscillation is coming from the edge effect of the toy model, because toy model is not the solution of the equation of motion. It's just something we designed. Actually, we didn't. People designed. Okay. So it is like putting three pieces together, and we think that the edge of this connection, because there is no in the derivative of it, there is no continuity equation, and we think that this lack of continuity of the derivative created these oscillations, because in any other solitonic model we never saw these oscillations. The only one we saw it was with this toy model. So you can see that interestingly. Okay, so you have for each parity and you have for the scattering, which is the one observable. Okay, you can see that there is cusp always at specific points, and these points are exactly the points the bound state passes the fermion energy equals 0, the E equals 0 line. Okay, which is really interesting result. It shows that the system doesn't like to pass this point. Because if the energy is higher, it means that it's not preferential for the system to pass this state. Okay, but we know that the fermionic zero modes are really important modes. They are related to the topology of the system, and they are quantum effect. And because of that, actually, in this kind of system, we saw that they are energetically unfavorable. It was interesting to see. Okay. So you can show that exactly at these values, there is one bound state passing the line E equals 0 for the fermionic system. Okay. Then we see the same thing. That was as a function of the value of the boundary, the theta 0. This one is as a function of the slope in the middle, the slope of the soliton in the middle. Again, you see these oscillations for the toy model, but for each parity, but when you put them together, you sum them for positive and negative parity, again, it will be smooth function. So physically, there is no oscillation here, okay? And again, there is a large peak here, exactly when one fermionic mode passes the line of E equals 0, okay? Again, you can see that this is not what system like to be in this configuration, okay? At least in the system we have, which has charge conjugation symmetry, parity symmetry, but doesn't have energy reflection symmetry, obviously, because you saw the spectrum is not symmetric from top or below, okay? At least in this kind of system, we are seeing that this is the configuration that the system doesn't like. Actually, it would be interesting to observe this in the system that has energy reflection symmetry, which is the energy of the system is symmetric with respect to the E equals 0 line, okay? Top and below to be symmetric. Okay, so So then we observed that this is summarized what we got. So we saw these oscillations, which was the edge effect. And then, for example, we saw in the Casimir energy as a function of the slope of the soliton in the middle, for mu equals 0 goes to 0, you can show that, okay? It goes to 0, which is non-trivial, because mu equals 0 is not exactly the trivial solution, right? Because at the boundaries, at infinity, still the theta 0 is non-zero, okay? So making it flat doesn't make it trivial vacuum. There is some residual thing at the infinities, but it seems that it doesn't have any impact on the Casimir energy. And you can show that when theta 0 is multiple of pi, integer multiple of pi, at infinity goes to 0 also, which is highly non-trivial, but for example, for the toy model, we proved it analytically. So this is what happens actually. So this is the thing we did in this work, okay? In this line of work, fermion interacting with the soliton, we did another work which is really recent. This is from this year, okay? Looking at the fermion field, if there is interaction between the solitons, so the background system is not static anymore, it's dynamical, okay? But then we know that if if solitons, they collide in 1 + 1 dimension, each individual one respects BPS condition, the one that I showed you. The first order equation solves the second order Euler-Lagrange equation, which is always valid, I said, for 1 + 1, but this is always valid for one individual soliton, okay? But if you put more solitons together, you see that it loses this characteristic. So it doesn't saturate the BPS condition, okay? Recently in the literature appeared an interesting model to keep part of this BPS condition, to saturate half of this BPS condition. So they introduced the concept of impurity. What is impurity? Impurity is you introduce a field, okay, here, like this sigma field here, which doesn't have dynamics. So it means that it is, if you, for example, they chose it to be in this form. If you put it here, when the sigma doesn't have dynamics, obviously it breaks the translational invariance, okay? So you break the translational invariance, okay? This is the cost, but you gain the BPS saturation, which is the gain, which is partially you protect the system against the decay, okay? Because it has to do with the stability of the system, okay? So we chose 5 for kink or 5 for model here with this impurity locked at 0, because the cosine here it's at x = 0, okay? Then why it is chosen in this shape? Because we want to guarantee that there is a kink solution, okay? Although the kink solution loses the translational invariance, so if you change x to x minus x0 and x0 non-zero, this is not the solution of the system anymore. So you could have kink just on top of the impurity, okay? But the anti-kink follows the BPS condition, so because of that we say that it is half BPS preserving, because anti-kink preserves BPS condition, but the kink doesn't. So then you will have a moduli space of these x0s. It can be many different x0s, okay? And then we want to see that when there is collision, for example, between anti-kink and the kink in the system, for example, what happens to the fermion interacting with them, okay? Still, the solitons are background for the fermion field. So the solitons won't see the effect of fermion, but fermion will see the effect of the solitons colliding. So this is, you can see three typical soliton solutions that we have. You can see that in the middle, in many cases, this is the three of them is just changing the initial condition, okay? So you can see that appears many times this bump or called lump in the middle, okay? So this is anti-kink. This one looks like anti-kink, kink, anti-kink, but then when you move it to the left, the anti-kink, you see that the bump separates but still stays on impurity around the center, okay? And when you take it to infinity, this blue line, it is just the lump. Okay, then we can have two different types of lumps. It can be at infinities having the value -1, or we could have on top to have value 1 equals 1. We call them L plus, L plus and L minus, okay, these lumps. Now let's see what we can do with the system. So first, from the Lagrangian, we can write the Euler-Lagrange equation, choosing one representation for the gamma matrices for the Dirac equation, and then writing the spinor field in components, and then making a change of variables. You can decouple the equations. Now, instead of first order equation, you will solve second order but decoupled. Here is first order but coupled. Psi 2 and psi 1 are coupled. Okay, so then it is like the soliton acts as this kind of potential in the Dirac equation. Okay, or exactly in the Dirac equation. So it is like Schrödinger-like equation with this specific potential, and the form of this phi is dictated with the background solitons colliding, that they have dynamics. Okay, so you can see here two different scenarios. One of them, if the collision is smooth, stays close to the BPS saturation point, so stays close to BPS condition, which is this first one. When anti-kink collides with a lump and survives a lump and anti-kink, okay? Then you can see that when lump with the anti-kink collides, you will have oscillating lump and anti-kink leaving, okay? And here you have anti-kink here, separating these two regions, and the kink on impurity. Kink just can be on impurity because we chose the impurity to trap the kink at the origin, okay? And then you can see that there appears oscillating kink and this anti-kink leaving, okay? This is what Fermion will see in the system when these two things happening, okay? You can see that at first we put Fermion field bound to the anti-kink, which is the BPS one, okay? So we bound with the zero mode. We choose always the zero mode of the fermion bound to anti-kink, and then when there is collision, we want to see where the fermion goes. Okay, then you can see the fermion transfer or stays in the same anti-kink, stays on the anti-kink, or excites but still stays on anti-kink, or it goes to the lump, or the other case goes to the kink, the zero mode or excited state. Okay, so this is how fermion behaves. So to see how we can measure, how we can quantify this fermion transfer, you could use Bogoliubov coefficients that simply calculates the overlap. Okay, it is measuring that what you, I think it's easier here to see that what you give as input, like the fermion attached or bound to the initial soliton, we call it J, okay, and then how after the collision the fermion will be on which soliton called K. Okay, so this measures the overlap or the amount of fermion transferred, or if you look at it as the number of fermions transferred. Okay, so you could look at these Bogoliubov coefficients as a function of time, how they evolve. This is the one when anti-king collide with the lump and survives anti-king and lump. Okay, and this the other one is when the anti-king collides with the king on impurity. Okay, and then you can see that the Bogoliubov coefficient for anti-king staying on anti-king is given by alpha. Bogoliubov coefficient anti-king transfers to king is given by beta. Anti-king doesn't transfer, stays on anti-king just to be excited mode, okay, is given by gamma. Here it's anti-king transfers to king but to excited mode, and this Bogoliubov coefficient when fermion bound to anti-king transfers to the lump, okay, where we showed it with psi. Okay, so in the BPS case, you can show that this is for a non-relativistic velocity. Okay, if you stay in non-relativistic regime, which means that we are working with natural units. So if you stay below 0.1, below 10% of light velocity, you can see that most of the fermion field will stay on the original anti-king, okay? Because it is, you can show that it's adiabatic. So while the BPS anti-king is spanning the moduli space with this x0, gradually fermion field will adjust and still bound to this anti-king, okay, changes smoothly the configuration, but doesn't excite or doesn't get transferred to another soliton, okay. But in this case, it is not BPS, okay. So everything is much harsher. Really fast, the system detaches from the original anti-king, the fermion field detaches, and you can see that the interesting point here is that you can see this orange line here is negatively correlated, or yes, negatively correlated with the red one, okay. The orange one is the beta squared, which is anti-king transferred to the king, the fermion transfer to the king, okay, and the red one is the delta, which is anti-king still transferred to the king but get to the excited state, okay. This is because this is actually the source of it is coming from this, because the final king is not a static king. It's neither static king nor a boosted one, okay. So the fermion field, the final fermion field, is not eigenstate of this the system with the king or the boosted one. Because of that, start oscillating between the two, okay. So this is the interesting result here for the Bogoliubov coefficient as a function of time. But we can do differently. We can fix the time and look at the Bogoliubov coefficients as a function of the parameters of the system, which is the coupling between the fermion and the soliton, and the velocity, showing different colors shows different velocity. So if we are working with really low velocity, we are in the adiabatic regime. For the case of this is the case of the BPS case, the initial configuration is BPS, okay. So if the velocity is small, we stay in adiabatic regime, so the system stays on anti-king, except for large G. When the coupling is really large, obviously easily the system goes out of the any perturbation can have high impact, so it goes out of the adiabatic regime, okay. So you can see that So this is for the adiabatic case, but when you increase the velocity, you go to the relativistic regime, and in the relativistic regime, it's much easier to detach from the original soliton and go to the other existing soliton at the end in the asymptotic future. Okay, and this is the interesting part. If you sum all these Bogoliubov coefficients, in the adiabatic case, the sum is almost 1. So it means that the system doesn't go to higher excited states or be lost as radiation. This amount is that low that is not observable here in the graph, okay? But when you go to a relativistic regime, this is highly non-trivial, because then the system becomes much more, it doesn't stay bound to the BPS, so it is farther from the BPS regime. Okay, so the system will lose, in this case, the probability to go to higher excited state or to be lost as radiation is much higher. In this case, yes, exactly, the higher excited states or the radiation effect, it's exactly the difference from 1, because we have the conservation of the probability, okay? So this was for the BPS case. This is for the non-BPS, that you can see that the system is much more sensitive to the parameters of the system, okay? And you can see that the sum of the coefficients is rarely close to 1, okay? So the system loses energy with the higher excited states or with the radiation, and the system is much more sensitive to the parameters of the system. So this was the study that we did this year with the instead of looking at static kink, looking at the dynamical kink collisions with the kink anti-kink and kink and lump in the system. There is another work that we did this last year and is published this year, which is again Fermion-Soliton interaction, but in higher dimension, in 3+1 dimensions. Okay, so we are complicating the system. Actually, this computation was extremely difficult and took a long time to do. It is considering the fermion field in the space-time of Dosite, which is a curved space-time, but one of the best curved space-time you could imagine, because it's maximally symmetric. It's maximally symmetric vacuum solution of Einstein equation, okay? And it is conformally flat. So with this conformal transformation, you can see that it is conformally flat. With this conformal factor, the rest is the Minkowski, okay? And we, besides looking at the Dosite space-time, looking at the fermion, how it behaves, what is important for us is the fermion cosmic string interaction. So cosmic string, we know that what it creates, it's the conical structure in the space-time, which means that the phi, the angle here, doesn't go to 2 pi. It is, depending on the value of the Q, it goes below 2 pi. And when Q is 1, we recover Minkowski. So this was it was our check to see we recover the Minkowski result that already studied in literature or not, okay? So we have Dosite space, so we have non-trivial geometry of Dosite, because Dosite is in 3+1 is simply connected. It is it's not a topological space-time. I mean, the whole thing appearing is geometric. Okay, it's the effect of geometry. But the effect of the cosmic string here is a topological effect. So we could study the effect of both on the fermionic vacuum. Okay. Besides that, we considered the effect of, so we considered a cosmic string, but we considered a magnetic flux passing through it. Okay. So what is more interesting for us in this space-time, which is relevant space-time in cosmology because it is with positive cosmological constant, so it explains the expansion of the universe, so it's interesting space-time for us, okay? So, but what is more important for us is putting the string in this space-time, and then a magnetic flux passing through it, and then we want to study the effect on the fermionic vacuum, okay? We actually, in this work, we studied the effect on the energy momentum tensor, so all components of the energy energy momentum tensor. But what I'm showing here is just the energy part, because it is more relevant for the Casimir energy that I showed before. So we have the Dirac equation. Obviously, we are working with the curved space-time, so we have the effect of spin connection here, and we have the U1 symmetry, so we have this gauge freedom, so we do this gauge transformation, and instead of working with this Dirac equation, we simply work with this one, where the psi field has the effect of the gauge directly here as the exponential. So I'm not going through the detail how we found these fermionic states, but you can find the fermionic states, and you see you can see that the time part is not trivial, because the City space appears that the exponential here with the time appearing here, okay? So you couldn't simply have ansatz as exponential of I times energy times time, okay? In this case, actually, it's highly non-trivial, and it's special function, Hankel function. And this is, in R, is Bessel function. So in this work, you need to work with many special functions, okay? So these are the parameters of the system, so we don't have time to go through the detail of this. But what is relevant here, the magnetic flux here over the quantum flux, you can show that there is a Aharonov-Bohm effect here, okay? Which means that the observables, the physical observables, they are dependent just on the fractional part. The integer part doesn't matter. Exactly like the known Aharonov-Bohm effect, that you put imagine you have a cylinder that the magnetic field is non-zero, but you are passing the electrons from both sides, and you want to calculate the interference. But if this division is integer, you won't observe the interference pattern. So the only thing that the only chance is to have some fractional part here, okay? And then we will show that all the physical observables will be dependent on this A0 factor. So what we did was to find the energy momentum tensor in the vacuum, the expectation value in the vacuum. This parenthesis is just symmetrization, it's nothing special, okay? And then we had this, we introduced this compact form for the sum over quantum numbers. In practice, you need to work with many integrals and sums here, okay? That they are related to the momenta, to helicity, and the magnetic the magnetic moment in the direction of the cosmic string that creates this quantum number J. So in this case, we calculated, I'm showing just the result for T00. This is the relevant one for the energy of the system, okay? The energy. Here, we just talk about the energy density because we are working with infinite string. So when you talk about infinite string, the energy of the system is always diverging. What you can talk about is the energy density only, okay? So, so here you need to manipulate many things. So I don't have time to show this. Then you play with these whole special functions, and then what is important here is that you need to separate the trivial part, which is the divergent part, coming from the pure de Sitter space, okay? So we are not interested on that infinity, okay, of the de Sitter space. We remove this divergence, okay? And we look at the rest for the effects of the cosmic string and the magnetic flux passing through the string in this spacetime. So This is the detail of the calculation. Then you can study when you are really close to the string, what happens, and when you're really far from the string, what happens. And we know that the string is a singularity in the space-time, so many things diverge at the point of the string, okay? And in this specific case, it is true also. So the energy density, the expectation value, is diverging on the string with 1/r⁴, okay, is diverging. And when you go really far from the string, it decays with 1/r⁴, okay? Also oscillating if the fermion is massive. You can, to simplify this whole thing, you could put massive all 0 and see it is just simply decaying. There is no oscillation. Okay, but this is interesting because in the Minkowski case, it goes exponentially to 0. The value here, but in the case of the Dosite, it becomes 1/r⁴. And another interesting part here, in this close to the string, you see that there is no effect of mass. So it becomes mass independent. It could be massive or massless when you get really close to the string, okay? So you can see the result for specific values of A0s, which is the fractional part of that magnetic flux, okay? And fixing this Q, which, as I said, this Q encodes the information about the string. So this first one is as a function of the distance from the string, and you see that when you get close to string, it diverges. And the right one is as a function of mass. So when you, in the beginning, it gives for the massless fermion, okay? So this is, actually, I think I talked about all these points here. So I think I'm done with the subject. So thank you. If you have any question, I'm here to answer, if I can. Mm-hmm.
Estou ligando aqui, um momento. Minha câmera está desligada. Questões, localizando webcams. Iniciar aqui.
Ok.
Ops. Acho que entrou aqui. Eu não estou vendo nenhuma questão aqui no notas compartilhadas, é isso? Mas eu tenho questão.
Agora fica difícil, né? Vamos.
Claro, tem bastante detalhes de cálculo, não dá para seguir tudo.
Uhum.
Certo? Mas eu fiquei curioso, não agora no string, mas eu fiquei curioso como é que você definiu o vácuo para o efeito Casimir na primeira vez, com o kink lá. Então, essa eu perdi. Você me entende? Entende, né? Assim.
Sim, exato. Ok, quer saber? Vamos voltar. Acho que fica mais fácil.
How the vacuum was defined, the non-trivial vacuum was defined to introduce the Casimir effect. I don't know how you proceeded with the vacuum. The vacuum was omega, you know?
Yes, the vacuum is actually, this is the interesting part of it, that it is not actually relevant. It doesn't matter the form of the vacuum. You just simply use the annihilation and creation operators, and you know the effect on the vacuum, okay? And you know that the energy should extract, the Hamiltonian should extract the energy of the system. This is exactly what we did. The most of the terms, they just simply canceled because you had for example, A dagger, or you had AA, and you know the definition of the vacuum is that is annihilated by A operator, right? So we simply use this condition. So it removed all the terms, okay? And here in the rest, it took out just the energy of the system, because we know that the Hamiltonian, it takes out the energy of the system, right?
Right.
So we didn't need to know the detail of the vacuum. This is actually the interesting part, that it really doesn't matter.
Yeah, this is new for me, because in order to calculate the Casimir effect just below your transparency, yes, okay. You have to subtract the free vacuum and the free energy, right?
Yes, you do the exact same thing. So you write it with the eigenfunctions here for the continuum, and the energy it is the Hamiltonian extracted. Okay.
Yeah, that's
the only term surviving. So you use again this the algebra between these operators, AA dagger operators.
Acting on the vacuum.
Acting on the vacuum, exactly.
Yes. Well, it is.
But if you are interested, then I could send you, more detailed version.
I would like to
okay.
see more games. It would be interesting.
Okay.
Another question is the following: is why did you call the sigma as impurity? This is a static external field only, isn't it?
It is, exactly.
It's a name or
impurity, because if you have like impurity in a system, what do you expect from impurity? It's like a spot in a system that doesn't move, right?
Yes.
So
right.
it is imposed in the system, okay? So it doesn't have its own character. It doesn't have its own dynamics.
Yeah.
Just exists to bother the others, but in this case, actually, it is nice.
Just a name, more or less, similar to impurity or something like that.
Exactly. I think the name is coming from like the impurity, in physical world.
So on. And tell me one thing: have you been studying the Gross-Neveu model? Because the Gross-Neveu model is the lambda, is like a Fermion, a lambda phi 4 for Fermion. You know that?
Yes, I know that, but I never worked with this model. But what is special about it that you are interested here?
I see. That's right. It is okay. But it is very nice working. Very nice. I told it to people that they.
Thank you. I hope you liked it. It was possible to follow.
It's quite nice. It's quite very, very nice. Quite bright people work, by the way. Yes. I don't know. Here there is no answer, no questions.
Okay.
Then I would like to thank you again and we keep in touch. If you can send me some of the things, in particular with the Casimir effect, I really appreciate.
Sure. I can send at least these two works that I put here. I have some more in this line that it is around like 4 or 5 years ago, from 4 or 5 years ago. I could send you.
All right.
Yeah, I would like to keep in touch, even if possible to collaborate. Maybe we can.
Thank you very much, and have a good night, and take care with the
Thank you.
sanitary situation with the pandemic is already here, and we keep in touch for sure. Oh, there is one question here.
Oh, okay.
Congratulations. I'm very interested. I think you can see that. Interested in applying non-extensibility ideas.
I don't have the link here with me to see in YouTube.
You don't have that.
No, I don't have it here.
I can read it for you. Congratulations. I agree with the congratulations. This is Bruno da Costa. He say, I'm very interested in applying non-extensibility ideas to fermions. Does AZNO have any work that has been studied on the formations in fermion from Thales statistics? Do you know that?
No, I'm not familiar with that. If I understood, in statistics, what exactly they do?
They were, well, Bruno cannot explain. Well, they use no extensibility. It's a kind of a deformation.
Okay.
They using the original algebras. These, I'm not familiar in case of fermions, me neither.
Yes, I don't know that, but
I know the Thales statistics and the deformations that they produce and so on and so forth. But
yes.
if I remember,
Yeah, then people should think that if it is relevant, the presence of the fermion in this kind of system or not. I don't know in this kind of system it is relevant or not. Because, for example, if you are working with superconductivity, the Cooper pair is pair of like electrons, so the fermion field is relevant here.
yeah,
Okay.
that's right.
But in the other one, you should see, I don't know, in this kind of system, does it match any physical system or not? I don't know.
Yes, neither. I'm quite familiar with the Grosnevy model, but if I can't remember, I don't know. I'm really not familiar with the statistics. The notion of non-extensivity applied to the Grosnevy model. I really don't know.
Yes, I don't know.
The standard one and so on. In this case, not. Yes. Maybe it would be interesting. I don't know.
Yeah, maybe.
Maybe. Well, thank you very much again.
Thank you.
It was a pleasure to be here with you. And for
Pleasure was mine. Thank you.
Yes, certainly. Have a very good night for you, for
You
your
too.
family, your people in Pernambuco. Bye-bye. Take care.
Bye-bye. Thank you. You too. Bye.
Muito bom.